The next challenge we will discuss is that of making things more energy efficient. As you can see here on this graph from DOE, we use a lot of energy for transportation, a lot of it for industry and manufacturing. But maybe somewhat surprising, a big chunk of our energy is used just by buildings, through buildings, commercial and residential buildings. So if we can make a dent in making these things more energy efficient, maybe we can really cut down on our energy use. Now, there's inspiration for this in the insect world. For instance, termite mounds are very energy efficient. This is a termite species mound that is in Australia. They built their mound in such a way, this is probably about twice man-sized height, and they built their mound in such a way that during the hottest time of the day, the sun is just facing the side of the mound, whereas during the cooler times of the day, it actually faces, the sun may face the mound head on. So in that way, there are differences in how hot the mound is during the day, at different times of the day. Also, this is from a termite species in Africa. Here is a termite mound that they put some gypsum or something in there and then took all the dirt off, and this is what the inside of the mound looks like. These mounds can be maybe 100 years old, and we're talking millions and millions of termites within this mound. And you can see, compared to this lady, this mound is huge. And then inside the mound, there's lots of galleyways and openings to the outside that the termites can close and open to their liking. And why do they have these mounds? Well, primarily because inside they have brood, their brood where they lay their eggs and where they take care of the young, plus fungus gardens. Actually, termites are gardeners, and they have these fungus gardens inside the mounds, and that is the fungus that they eat. But the brood and the fungus needs to be a certain temperature, so they come up with this passive cooling system where they can control how the temperature, the CO2, the humidity inside by just opening and closing certain galleys that may be really close to the surface, further away from the surface. And they do this by just covering holes with dirt or feces. So this system has been applied probably most famously by an architect from Zimbabwe, and he designed and got built this huge building in Harare, Zimbabwe, which is made up of this terracotta stone that is local. Plus, it doesn't have an AC system because the floors under each floor is hollow, so air can go through, and then we have these big fans that push air up and through the building. And this, the architect claims that he was inspired by termite mounds, the local termite mounds for this building. And because there's no AC system, just the building of the building was only 10% of the regular cost of a regular building, and then now the upkeep, because there's no AC, is also a lot cheaper. Not sure what things look like now. Things, as we speak now in 2009 in Harare, are not very quickly stable, but they did get this building built. It is also a little bit cumbersome because of they have to have there's no elevator from one floor to the next because that would impede the airflow. So there's elevators going to a couple of floors, and then they have to go to another elevator. But the cost of building it and maintaining it is a lot less.
The challenge is, how can we capture enough abundant clean water to sustain our population?
The supply of fresh water is under rapidly increasing pressure.
due to population growth, land use changes, the deterioration of water quality. Every time you use it, it may get a little dirtier, and due to climate change. The inspiration for how we may be able to capture water from sources where we previously have not captured it is the Termite beetle. The Termite beetle lives in Libya, which is a very dry area, a lot of desert. However, it is on the ocean, and in the morning there may be a fog rolling in from the ocean onto these sand dunes where these Termite beetles live. And they are able to capture water from the relatively moist air during those few hours that there is moist air. As you can see here, it gets really, really hot during the day. And these beetles actually raise their bodies to not get too hot. But the way to do this, we capture the water, the key is that you have to catch enough of these little droplets of water to make one big droplet that will roll down and into the mouth of the beetle. And they do that by standing at a certain angle against the winds, and then the wings, in this case they're called the elytra, the wings of these beetles, have both hydrophilic valleys and hydrophobic valleys and hydrophilic bumps. So the water keeps collecting into bigger and bigger droplets because they're getting pushed away by these bumps. And meanwhile, because of the position of the beetle, they roll down the head of the beetle into the mouth, and that's how they drink. So maybe we could use materials that can harvest water, maybe even add some self-decontamination material to that surface. And they have accomplished this by creating these surfaces that have hydrophilic valleys and hydrophobic bumps, and then these water droplets aggregate, and if you put the material at a certain angle, it will roll down. And here's another side example of where you spray small droplets and then they will accumulate on the patterned hydrophilic area shown here. And this is work done at MIT. Oops. The way we could maybe use this is, as I said, creating surfaces, maybe kitchen counters or in hospital surfaces that can clean themselves, but also maybe in certain areas in the world where you have relatively moist air, you can collect the water and